Picture two towns, same country, same healthcare system, same general culture. One sits near the coast, barely above sea level. The other sits high in the mountains, thin air, short of breath just walking up a hill. On paper, the mountain town sounds harder to live in, less oxygen, colder winters, harder physical conditions. But look at the actual data, and something strange shows up. People in that mountain town tend to live longer. This isn't a one-off curiosity. It's a pattern researchers have documented again and again across very different parts of the world. And it raises a genuinely interesting question. Does thin air actually help you live longer? Or is something else going on, hiding underneath the numbers? Let's start with where this idea comes from. In one of the most detailed studies of its kind, researchers at the University of Colorado, working with Harvard's School of Public Health, spent 4 years combing through death certificates from every county in the United States. They looked at cause of death. They looked at socioeconomic factors. They looked at elevation. What they found was striking. Of the 20 U.S. counties with the highest life expectancy, most were in Colorado and Utah. Every one of them sat at an average elevation of nearly 6,000 feet. Men in these high-altitude counties lived 1 to nearly 4 years longer than men near sea level. Women lived about half a year to 2.5 years longer. That's not a small effect. Over an entire population, a few years of extra life expectancy is a meaningful shift. This pattern isn't limited to the American West either. Researchers studying populations in the Andes have found lower rates of heart disease and certain cancers at elevations above roughly 11,000 feet. Indigenous populations in Tibet show similar patterns of adaptation and resilience at extreme altitude. And a large study following over 150,000 people in the Colorado Rockies found consistently lower mortality rates compared to people living at sea level. So what's actually happening at altitude that might explain this? The starting point is simple physics. As you climb higher, air pressure drops. That means every breath contains fewer oxygen molecules than the same breath would contain at sea level. Your body notices this immediately, and it responds. One of the first things that happens is a rise in a hormone called erythropoietin, usually shortened to EPO. This hormone tells your bone marrow to produce more red blood cells. More red blood cells means more oxygen-carrying capacity in your blood, which helps your body compensate for the thinner air. This is actually the same mechanism elite endurance athletes try to exploit through altitude training, sometimes called live high, train low, specifically to boost their oxygen-carrying capacity before a competition. But the adaptations don't stop with more red blood cells. Chronic low oxygen exposure appears to trigger changes at the cellular level too. Research has shown that mitochondria, the tiny structures inside your cells responsible for producing energy, actually become more efficient under sustained low oxygen conditions. Your body essentially learns to do more with less. There's also a specific molecular pathway involved, centered on something called HIF-1 alpha, short for hypoxia-inducible factor. Under normal oxygen conditions, this protein gets broken down quickly and doesn't do much. But when oxygen is scarce, HIF-1 alpha builds up and switches on a whole set of genes. Some of those genes help form new blood vessels, essentially building extra highways for blood to reach tissue more efficiently. Others help regulate metabolism itself. This last part turned out to be more interesting than researchers initially expected. A study published in the journal Cell Metabolism looked specifically at how chronic low oxygen exposure changes metabolism in mice. The mice exposed to low oxygen conditions processed sugars and fats differently than mice breathing normal air. This may help explain a pattern researchers have repeatedly observed in high-altitude human populations: lower rates of diabetes, lower rates of high cholesterol, and lower rates of obesity compared to populations living at sea level. There's an even more dramatic version of this finding from a Harvard-led mouse study. Researchers placed one group of mice in a chamber with normal oxygen levels, and another group in a chamber with oxygen restricted down to a level similar to the summit of Mount Everest. The mice with restricted oxygen lived, on average, 24 weeks. The mice breathing normal air lived 16 weeks. That's roughly a 50% increase in lifespan, in a controlled laboratory setting, driven entirely by reduced oxygen availability. At this point, it's worth pausing, because this is exactly where a story like this can get oversimplified into something misleading. Before we get to the human population data, there's a fascinating wrinkle worth mentioning. Not everyone living at high altitude got there the same way, biologically speaking. Populations that have lived at extreme elevation for thousands of generations, particularly in Tibet and the Andes, show genuine genetic adaptations that newcomers simply don't have. Tibetan populations carry a specific gene variant inherited from an ancient human relative called the Denisovans that helps regulate how much extra hemoglobin their bodies produce in response to low oxygen. This matters because too much hemoglobin, thick, sluggish blood, can actually become dangerous over time. Andean populations appear to have arrived at a different genetic solution to the same problem, involving how efficiently their tissues extract oxygen from blood, rather than simply making more of it. This is a useful reminder that living at altitude isn't one uniform biological experience. Someone whose ancestors adapted to thin air over thousands of years is working with different underlying biology than someone who moved to Denver 5 years ago. Most of the population studies showing longevity benefits are looking at the second group, people living at moderate altitude without deep generational adaptation, which makes the mechanism, cardiovascular and metabolic adjustment through EPO and HIF-1 alpha, even more relevant to an average person considering whether altitude might matter for them. The same University of Colorado study that first identified the striking difference in life expectancy also ran a more careful analysis. When researchers statistically accounted for socioeconomic factors, solar radiation, smoking rates, and pre-existing pulmonary disease, something important happened. The net effect of altitude on overall life expectancy became negligible. Read that again, because it matters. The raw numbers looked dramatic. High-altitude counties genuinely do have longer average lifespans. But once you control for who tends to live in these places, and for other health-relevant factors that happen to cluster there, most of that apparent benefit disappears. Think about who actually ends up living in a Colorado mountain town versus a struggling former industrial city near sea level. These aren't randomly assigned populations. People who move to mountain towns, or who can afford to stay there, often skew toward higher income, better access to healthcare, and lifestyles built around hiking, skiing, and general outdoor activity. None of that has anything to do with oxygen levels, and all of it independently predicts a longer life. A statistician would call this a classic case of selection bias layered on top of a real biological signal, and separating the two cleanly is much harder than the initial headline numbers suggest. This is a textbook example of something researchers call a confounding variable. There's a second complication too, and it's an important one. Altitude's relationship with health isn't a simple straight line where higher is always better. A detailed narrative review looking at mortality data across multiple countries found that while higher altitude is associated with lower mortality from cardiovascular disease, stroke, and certain cancers, it's associated with higher mortality from chronic obstructive pulmonary disease and lower respiratory tract infections. In plain terms, thinner air seems to help your heart and blood vessels, but it can be harder on already compromised lungs. The same review suggested something worth sitting with. Moderate altitude may be more protective than extreme altitude. There appears to be something like a sweet spot, somewhere in the range of a few thousand feet, past which the benefits start trading off against new risks. Extremely high altitude, the kind found on major mountain expeditions, isn't simply more of a good thing. It introduces its own set of physiological stresses that can outweigh the cardiovascular benefits seen at moderate elevation. This U-shaped relationship shows up in other altitude research too. One study looking at critically ill COVID-19 patients found notably better survival rates among those treated in a high-altitude intensive care unit compared to a sea-level unit, with researchers proposing that better oxygenated tissue and altered ACE2 receptor activity might play a role. It's an interesting, if narrow, data point, but it also illustrates how altitude research tends to produce findings that are context-specific rather than universally applicable. What helps in one scenario, one condition, one population, doesn't automatically generalize to every health outcome researchers might care about. There's also a subtler explanation researchers have proposed that has nothing to do with oxygen at all. Higher altitude generally means higher solar radiation exposure, more direct sunlight, which supports better vitamin D synthesis in the body. Vitamin D has its own documented associations with cardiovascular health and immune function. It's entirely possible that some portion of the longevity pattern researchers keep finding at altitude isn't really about thin air. It might be about sunlight doing its own separate, well-documented job. Interestingly, this same sunlight factor cuts both ways. More UV exposure at altitude means a higher baseline risk of skin damage and certain skin cancers, even as it may be quietly supporting cardiovascular health through vitamin D. It's another reminder that almost nothing about altitude's effect on the body reduces to one single clean variable. Oxygen, sunlight, activity level, income, and lung health are all bundled together in ways that resist tidy separation, which is precisely why researchers still describe this area, after decades of study, as inconsistent and worth pursuing further rather than settled. So where does the evidence actually leave us? The honest picture looks something like this. There's a real, physiologically plausible mechanism by which chronic mild oxygen restriction could support cardiovascular health and metabolic function. The mouse studies are genuinely striking, and the molecular pathway involving EPO and HIF-1 alpha is well understood and consistently reproducible in the lab. That part of the story holds up. What's much less certain is how much of that translates into a meaningful, altitude-specific longevity benefit for an average person moving to a higher elevation. The human population data is consistently confounded by lifestyle, wealth, activity levels, and sun exposure, all bundled together with elevation in ways that are hard to fully separate. And the dose matters. Moderate elevation looks protective in some ways. Extreme elevation introduces new problems, particularly for anyone with existing lung disease. This doesn't mean the altitude research is worthless or that the pattern is purely coincidental. It means the honest answer to, does high altitude extend your life, is something closer to, probably a modest, real physiological benefit exists for cardiovascular and metabolic health at moderate elevations, but it's tangled up with other factors, and it's not the dramatic 50% lifespan boost you'd get from reading only the mouse study headline. So what does someone do with this, especially if moving to Colorado or the Andes isn't realistic? The most direct, low-effort takeaway is this. You don't need to live at altitude permanently to get a small taste of the underlying mechanism. Spending time at moderate elevation, a mountain vacation, a hiking trip, a weekend somewhere in the 5,000 to 8,000 foot range does trigger some of the same short-term adaptations, including a temporary rise in red blood cell production if you stay long enough for your body to start adjusting, generally around 1 to 2 weeks. This is genuinely why endurance athletes use altitude training camps. It's a real, measurable physiological effect, just a temporary one that fades once you return to sea level. If you're curious about experiencing this without booking a plane ticket, there's a middle ground option worth knowing about. Some gyms and sports science facilities offer altitude training rooms, sealed spaces with artificially reduced oxygen levels that simulate elevations of 8,000 to 12,000 feet. Athletes use these to get some of the adaptive benefits of altitude training without traveling to the mountains. The evidence for meaningful longevity benefits from short sessions in these rooms is thinner than the evidence for actual sustained altitude exposure, so it's worth treating this as a training tool rather than a longevity intervention. Still, for someone specifically interested in cardiovascular conditioning, it's a legitimate, research-backed option that exists closer to home than the Andes. It's also worth being honest about who this entire conversation applies to. People with pre-existing heart conditions, lung disease, or certain blood disorders often need to be cautious about altitude exposure, sometimes significantly so. The same low-oxygen environment that appears to nudge a healthy cardiovascular system toward beneficial adaptation can place real strain on a system that's already compromised. This is exactly the kind of decision worth discussing with a doctor before a high-altitude trip, rather than assuming that because moderate elevation is associated with better outcomes in the general population, it's automatically safe for any individual person, regardless of their existing health status. For people who already live at moderate elevation, the research offers some quiet reassurance. If you've ever wondered whether the thinner air where you live is doing something notable for your cardiovascular system, the honest answer is probably something, though it's difficult to isolate from everything else about your lifestyle and location. For people who don't live near mountains and have no plans to move, there's a more useful takeaway hiding underneath all of this. The specific mechanisms altitude appears to work through, better mitochondrial efficiency, improved vascular function, more red blood cells carrying oxygen more effectively, aren't exclusive to elevation. Regular cardiovascular exercise triggers strikingly similar adaptations. So does, to a smaller extent, deliberately challenging your body's oxygen efficiency through structured training. You don't need thin air specifically to nudge these same biological systems in a favorable direction. Altitude is simply one particularly effective, naturally occurring way of doing it, not the only way. There's also a broader lesson buried in this story, one that connects to a pattern we keep coming back to on this channel. A striking population-level statistic, longer lifespans in mountain counties, dramatically longer-lived mice under low oxygen, can be entirely real and entirely misleading at the same time, depending on how carefully you dig into what's actually driving it. The mechanism can be genuine, the molecular pathway can be well understood, and the population-level headline can still collapse the moment researchers control for who actually lives in these places and how. That's not a reason to dismiss interesting findings the moment they get complicated. It's a reason to hold on to both halves of the story at once. Something real is likely happening in the bodies of people who live at moderate elevation for years. Their hearts may genuinely benefit from mild chronic oxygen restriction, through pathways researchers can trace all the way down to specific genes switching on and off. But the leap from that mechanism to moving to the mountains will add years to your life runs headfirst into a wall of confounding variables that researchers still haven't fully untangled, and probably won't for a long time, given how difficult it is to separate elevation from everything else that comes bundled with it. If there's a single, honest, actionable point in all of this, it's probably this. The biological pathway altitude exploits, pushing your cardiovascular and metabolic systems to adapt to a bit less oxygen than they're used to, appears to be a genuinely useful one. You can access a piece of it through regular vigorous exercise wherever you live. You can access more of it temporarily through a mountain trip. And if you already live somewhere high up, there's a reasonable chance your body has quietly been doing something beneficial with that thin air for years, even if science still can't tell you exactly how much credit belongs to the altitude itself and how much belongs to everything else about the kind of place and the kind of life that tends to come with it. If this changed how you think about the air you breathe every day, subscribe. Until next time, take good care of yourself.